Out in the open Pacific, something enormous was moving at jetliner speed, and almost no one could see it. Not ships, not people on the shore, not even most satellites. In deep water, a tsunami isn't a towering wall. It's a long, low pulse, sometimes only inches to a foot high, spread across miles. You could be on a boat directly above it and never know. Until one NASA instrument caught it in startling detail. Not a blurry hint, not an after-the-fact model. A high-resolution view of a tsunami in motion, mid-ocean, captured in a way scientists have wanted for decades. And once you see what it reveals, the bigger question hits hard. If a tsunami can cross an ocean almost invisibly, what else are we missing until it's too late? This story begins on January 15th, 2022, in the Kingdom of Tonga. The Hunga Tonga Hunga Ha'apai volcano erupts with extraordinary force. The blast drives a plume high into the stratosphere. A shock wave ripples outward and circles the globe. Then the ocean responds. Hours later, the sea surges into harbors. Boats slam into docks. Debris moves in violent, unfamiliar currents. Coastlines far from Tonga, Fiji, Samoa, New Zealand, Australia, Japan, and the Americas feel the effects. In Peru, rough seas linked to the event contributed to coastal damage and a deadly incident. One eruption, one remote location, and the entire Pacific Basin becomes part of the same emergency. For decades, the basic tsunami story has been taught as a straight line. A large undersea earthquake displaces the seafloor. A broad patch of ocean lifts. Gravity pulls it back down. Energy radiates outward as long waves. In deep water, those waves move fast, hundreds of miles per hour, but stay low. They become dangerous when they reach shallow coastal zones, where the energy piles up into surges and walls of water. That picture powers warning systems. It shapes computer models. It shapes what we think we're looking for. And it works most of the time. But the Tonga tsunami didn't behave like a textbook, quake-driven tsunami, because it didn't start with an earthquake. It started with a volcanic explosion, and that changes the rules. The eruption didn't just shove water. It launched an atmospheric pressure pulse, an air wave, that raced around Earth. That pressure disturbance can push on the sea surface, transferring energy into the ocean as it travels. So this wasn't only an ocean wave. It was a hybrid event. Ocean below, atmosphere above, with two systems coupled together at high speed. A simple way to understand the danger is resonance. Think of pushing a child on a swing. Push at the wrong rhythm, and the swing dies out. Push at the right rhythm, and each shove adds energy. In the open ocean, the speed of that atmospheric pressure wave can be close to the speed of a tsunami in deep water. When those speeds align, the atmosphere can keep feeding the ocean wave over long distances, sustaining it, reshaping it, and helping explain why this tsunami produced notable effects far from its source. That coupling is exactly the kind of complexity that can break assumptions embedded in warning systems built mainly for earthquakes. Now pause, because the next part is where the story becomes disruptive. Even without the atmosphere, the open ocean is not a smooth, uniform conveyor belt. It's layered with warm water above colder water, and density gradients that support internal waves and shifting currents. Add seamount chains, ridges, and continental slopes, and you get an environment that can refract, scatter, and focus tsunami energy. Scientists have long suspected that real tsunamis interact with all of that. But in practice, much of the ocean between the source and the shore has been a blind spot. Deep ocean pressure sensors are lifesavers, but they're sparse, and the Pacific is vast. Satellites offer global coverage, But traditional radar altimeters mostly measure along a narrow track, like trying to understand a painting through a straw. So for years, the middle of the tsunami story has been the part we largely inferred. Models stitched together with limited measurements. Until SWOT. SWOT, the Surface Water and Ocean Topography Mission, is a joint satellite led by NASA and the French space agency CNES, with contributions from the Canadian and United Kingdom space agencies. It was designed to measure water surface height with exceptional precision, and its key advantage is how it sees. Instead of sampling a thin line, SWOT uses radar interferometry to map sea surface height across a wide swath, producing a two-dimensional image of the ocean surface. Not a single thread of data, but an actual field of measurements. When SWOT's radar swept over the Pacific after the Tonga eruption, it captured the tsunami's signature etched into the sea surface, alternating ridges and troughs stretching across long distances. And the pattern wasn't the smooth, simple pulse we like to imagine. It was textured, with energy distributed across multiple scales, and wave features that suggest the tsunami was being shaped not just by the seafloor source, but by the ocean's internal structure and the atmosphere above it. In other words, SWOT didn't just confirm that a tsunami was there. It showed what it looked like in the open ocean, in motion, with details that older systems would have missed. That matters because coastlines don't simply get hit. They respond. Harbors can resonate, amplifying surges the way a musical instrument amplifies sound. Narrow bays can funnel energy. Continental shelves can lift a subtle deep water signal into a sudden, fast-moving hazard. Underwater topography can focus waves like a lens focuses light, turning a broad threat into a concentrated strike. That's why two places the same distance from a tsunami can experience completely different outcomes. And it's why "it wasn't that bad where I was" is never proof the event was small. It's proof the local geometry didn't amplify it. The Tonga tsunami also sharpened a hard truth about forecasting. Earthquake-driven tsunamis begin with information we can estimate quickly: magnitude, fault geometry, and the likely seafloor displacement. Volcanic blasts, landslides, and atmospheric disturbances are different. The initial water displacement can be uncertain. The plume evolves. The pressure field changes. The coupling between air and sea becomes a moving target in real time. SWOT doesn't solve that problem overnight. Satellites don't hover. They orbit and they pass over when they pass over. But what SWOT provides is something warning science desperately needs: ground truth. A direct measurement of the ocean's response that can be used to test models, improve the physics inside them, and expose where assumptions fail, especially for non-traditional tsunamis that don't fit the earthquake template. There's a broader implication, too. If SWOT can resolve subtle sea surface height changes across wide areas, it can also illuminate ocean currents, eddies, and storm surges, features tied directly to extreme weather and climate. Better ocean topography maps help scientists understand how heat moves around the planet, shaping hurricanes, marine heat waves, and regional climate shifts. So yes, this is about one tsunami. But it's also about seeing the ocean as it really is: layered, dynamic, and connected to the sky above it. And it's about what happens next. Turning high-resolution science observations into operational warnings requires rapid processing, open data pipelines, and agencies willing to integrate new streams into decision-making. It also requires humility, with systems built for surprises, not just for the disasters we've rehearsed. Because the most unsettling lesson of the Tonga event is not that a tsunami can travel fast. We already knew that. It's that a basin-wide tsunami can be driven by more than the seafloor, and that its energy can carry structure we didn't have the tools to see until now. Out in the open Pacific, a wall of water raced outward at jetliner speed, almost invisible. Almost. This time, we caught it. Its ridges, its troughs, its complexity, before it reached the shore. And that is the real meaning of this first high-resolution view. Not that the tsunami problem is solved, but that the ocean has shown us a truth we can't ignore. The next disaster may not look like the textbook version, and our safety may depend on learning to see the invisible fast enough to act, while the wave is still out there, moving in plain sight.